Welcome to Dr. A classes. Today we begin one of the most important topics in engineering geology, that is structural geology. Structural geology helps engineers understand how rocks behave under natural forces and why failures occur. As civil engineers, you will build dams, tunnels, bridges, and highways, and all of them interact with rocks. If we do not understand rock structures, we cannot design safely. So, today we'll learn how rocks deform, why they deform, and what structures are formed inside the earth. Learning objectives of the courses, understanding the causes of rock deformation and the role of Earth's internal energy, identifying different types of geological stress, compressional, tensional, and shear, analyzing the engineering significance of structural features, differentiating between elastic, ductile, and brittle deformation, relating depth, temperature, and pressure to rock behavior, applying structural geological principles in foundation, slope, tunnel, and dam design, evaluating potential engineering risks associated with geological structures. What is structural geology? Structural geology is the branch of geology that studies deformation in rocks. As you see on the far left of the diagram, we start with unstressed rock layers which serve as the baseline for understanding how the Earth's crust is reshaped. When rocks are subjected to forces inside the Earth, represented here by the large red tectonic forces that do not stay still, depending on the pressure and temperature, they will bend, break, tilt, or shift. These physical changes create the distinct architecture we see in the center and right of the image: folds, the arcs and troughs, fault when layers have physically slipped, and joints, the vertical fractures. Looking at the directional arrows in the diagram, it is clear these structures are not random. They are the precise geometric results of tectonic forces acting over millions of years, recording a history of whether the earth was being squeezed or pulled apart. Why do rocks deform? Rocks deform because of Earth's internal heat energy. As seen on the left of the image, the core acts as the primary engine, possessing the internal heat energy required to move the layers above. This heat generates convection currents within the mantle. The red and blue arrows in the diagram illustrate how heated material rises and cooler material sinks. These currents derive plate tectonic movements, shifting the massive slabs of the crust, that is lithosphere, shown at the top of the graphic. As the moving plates interact, they apply continuous forces on the rock masses, such as the compression and tension shown by the red arrows acting on the rock blocks. While these forces act slowly, they operate continuously over millions of years to gradually change rock structures and orientation, resulting in the folding and faulting shown in the macro scale detail. Forces responsible for deformation. When tectonic plates move, rocks experience three main forces. Compression pushes rocks together, tension pulls them apart, shear causes rocks to slide past one another. Each type of force produces distinct geological structures. Rock behavior under applied forces. When forces act on Earth's crust, they create a stress, defined as force per unit area. This stress produces a strain, meaning deformation in the rock body. The deformation may involve changes in shape, size, or volume. The type of response depends on environmental conditions such as temperature, pressure, depth, and duration of stress. As shown in the top row, the direction of stress dictates the shape. Compression squeezes and thickens the rock, tension pulls it thin, and shear causes lateral sliding. However, a rock's breaking point depends on its environment. In the shallow crust, where temperature and pressure are low, rocks undergo brittle deformation, resulting in fractures and faults. Deep underground, where it is hotter and stress is applied over longer periods, rocks become plastic. This leads to ductile deformation, where the layer bends into the folds and the foliation you see on the right. Types of deformation. Depending on conditions, rocks may respond differently to stress. Diagram illustrates the mechanical behavior of rocks under stress, showing how environmental factors like depth, temperature, and pressure dictate whether the Earth's crust bends or breaks. Elastic deformation, temporary. In the first stage, rocks act like a spring. They absorb stress by stretching or compressing, but because the internal bonds are not permanently broken, the rock returns to its original shape once the pressure is released. Plastic or ductile deformation, that is permanent bending, as rocks move towards greater depth, increasing heat and pressure make them softer and more pliable, allowing them to fold and flow into permanent waves without snapping. Brittle deformation or fracturing. When stress is applied too quickly or the rock is cold and rigid, typically near the surface, it reaches a yield point where it can no longer deform elastically or plastically, resulting in rock breaks, which is known as faults. Comparison of deformation types. Let us compare the three types of deformation. Elastic deformation is temporary and reversible. The rock does not break. Ductile deformation is permanent but occurs without fracture. It is common at greater depth where temperature and pressure are high and it produces folds. Brittle deformation is also permanent, but here the rock fractures. It occurs near the Earth's surface and forms fault and joints. This comparison is very important for understanding structural behavior in engineering geology. Factors controlling rock deformation. Rock deformation is more than just a matter of force. It is a complex outcome shaped by environmental conditions. Temperature and pressure, high heat and intense confining pressure deep underground favor ductile behavior, allowing rocks to flow and fold. Conversely, low temperature and pressure near the surface promote brittle failure, causing rocks to crack or fault. Time and rate. The speed of stress is critical. When applied slowly over millions of years, rocks have the patience to bend. Sudden stress leads to instant shattering. Composition. The specific rock type and its mineral makeup dictate its inherent strength and how it reacts to these forces. Fluids. The presence of water acts as a lubricant and chemical catalyst, weakening the rock structure and making deformation much easier. Depth and deformation. The diagram maps the structural change of Earth's crust as it descends from the surface to a depth of 30 kilometers. Brittle deformation. Near the surface, cold temperature and low pressure makes rock rigid and prone to snapping like glass. Fracture and fault. Under tectonic stress, these rocks break along planes, resulting in faulting and release of energy as earthquake. The transition zone. At roughly 15 km depth, the increasing heat and pressure reach a tipping point where rock behavior fundamentally shifts. Ductile deformation. In the deeper crust, intense heat makes minerals more mobile, allowing rocks to behave like thick plastic or putty. Instead of breaking, these deep rocks undergo permanent folding and slow plastic flow, absorbing stress without fracturing. Structure formed by deformation. Earth's crust is in a constant state of motion, and how it responds to these forces depends entirely on the nature of the stress applied and the physical properties of rock itself. This process, known as deformation, is what shapes the architecture of our planet. Geological structures generally fall into four primary categories. Folding. When rocks are deep enough to be warm and ductile, they behave like plastic. Under compressional stress, these layers bend rather than break, creating the wave-like arches and troughs we see in the mountain ranges. Faulting. Closer to the surface, rocks are cold and brittle. When stress exceeds the rock's internal strength, it snaps. This brittle failure results in displacement. If the crust is pulled apart, it creates a normal fault. If it is pushed together, it results in reverse fault. Jointing. Not every break involves movement. Jointing produces fractures or cracks where there is no significant displacement. These are often the result of rock expanding as it is uplifted towards the surface or contracting as it cools. Cleavage and foliation. At the microscopic level, intense differential pressure can physically reorient the minerals within a rock. As minerals like mica align themselves perpendicular to the pressure, they create flat surface, that is cleavage, or layer banding, that is foliation, characteristics of metamorphic rocks. Importance in civil engineering. For civil engineers, understanding deformation is critical. Foundations must consider bedding orientation, slope may fail along weak planes, tunnel can collapse if they intersect faults, dam safety depends on the presence of fractures, structural geology directly affects engineering stability. When we design massive infrastructure like the dam and tunnel shown here, we are not just building on rock, we are building on a history of tectonic deformation. As you can see in the background, the bedding orientation of these sedimentary layers is heavily folded. For civil engineers, these curves are not just scenic, they represent potential failure points. If a foundation is placed on layers dipping away from the structure, it could slide. Look closely at the tunnel entrance and the dam abutments. We have to map every fracture and fault that intersects these sites. A tunnel that cuts through a weak fault plane is a tunnel at risk of collapse. Similarly, the safety of that dam depends entirely on the fracture networks within the rock. If those fractures are not identified and grouted, water pressure could bypass the dam or destabilize the entire slope. In short, we do not just build on the geology, we build with it. Field identification of deformation. Structural geology is best understood in the field. It involves analyzing the arrangement and deformation of rock formation. In the field, engineers and geologists actively examine rock layers to identify fractures and other structural features. A fundamental aspect of this work is measuring dip and strike. The strike is horizontal direction of a rock layer, while the dip is the angle of its tilt from the horizontal. Additionally, analyzing fold geometry is essential. Understanding how rock has bent or folded provides key information about the forces that shape the area. These combined observation and the technical skills are essential for making safe and informed engineering decisions. For example, identifying an active fault zone or a particular weak and unstable layer before building can prevent catastrophic failure. At the end of the presentation, these are self-assessment questions. Go through each question carefully, answer these questions based on understanding of the topic, review any concept you are unsure about. The questions are: why do rocks deform? Explain with reference to the Earth's internal energy. How do mantle convection currents lead to rock deformation? How does temperature and pressure influences the type of deformation? Why is understanding rock deformation essential for foundation design? Explain how slope failure may occur due to structural weakness planes. Explain how the same rock can show elastic, ductile, or brittle behavior under different conditions. Explain how knowledge of geological structures helps in reducing engineering risk. Thank you for joining this lesson on engineering geology today. Hope you found this presentation informative. So don't forget to like and subscribe the channel Dr. A Classes for more engaging lessons on core subjects of civil engineering. Thanks.